Here we have the function of the third root of x, or the cube root of x, and we want to find the area of the region bounded by the graph in the x-axis from 0 to 5. And so first we'll fill this region right here, shaded region, with rectangles, and then find what's called a Riemann sum. And that will approximate the area of the shaded region, and then we'll fill it up with an infinite number of rectangles and then find the exact area. So we want to get the Riemann sum, and so we'll partition the interval from 0 to 5 as follows. X of 0 will be 0, x of 1 will be 5 times 1 to the third divided by n to the third. X of 2 will be 5 times 5 times 2 to the third dividing by n to the third. The x of 3 will be 5 times 3 to the third dividing by n to the third. And so x of n will be 5 times n to the third dividing by n to the third, which is 5. And so x of 0 is 0, x of n is 5. And therefore, in general, if we x of I will be 5 times I to the third dividing by n to the third. And now let's look in an example where n is 8, and so we'll fill this shaded region with 8 rectangles according to this pattern of x of i's. And so here we have the shaded region with 8 rectangles, and so the x of 0 will be 0, x of 1, the first rectangle, the width is a little bit small, so it's a little bit hard to see it. This is x of 0, so it's 0, and then the x of 1 is 0.09765. And then x of 2, which is this one, and is 5 times 2 to the third dividing by 8 to the third, since n is 8. And that would be x of, that'd be 0.078, which is right here. And then next we have x of 3, which is 5 times 3 to the third divided by n to the third. And so it's 0.26, which is right here. And then the other x of y, and then x of 4 will be 0.625, and then x of 5 will be 1.2, x of 6 will be 2.1, and then x of 7 will be 3.34, and then x of 8 will be 5. And so x of 8 would be right here, and this is x of 7, x of 6, x of 5, x of 4, and so on. And now let's look at the width of each rectangle. And so the first width, it will be x of 1 minus x of 0. But x of 0 is 0, and so we get 5 times 1 to the third dividing by n to the third. And so it would be 5 over n to the third. And so if n is 8, then this would be 5 over 8 to the third, which is 512. So it would be 5 over 512. And then the width of the second rectangle, it would be x of 2 minus x of 1, and it'd be 35 over n to the third. And then the width of the third rectangle, it'd be x of 3 minus x of 2, and that would be 95 over n to the third, and so on. And so in general, the width of the ith rectangle, it would be x of I minus x of I minus 1. And earlier we found that since we're using this pattern right here for the x of i's, and then x of I in general is 5 times I to the third dividing by n to the third. And so in the place of x of I, we have 5 times I to the third divided by n to the third. And then x of I minus 1, we just replace the I with I minus 1. I minus 1 to the third, and if we use the binomial expansion, then we'll get I to the third minus 3I squared plus 3I minus 1. And then multiply this out, we get negative 5I to the third plus 15I squared minus 15I plus 5. And then 5I to the third minus 5I to the third is 0. And so what's left is 5I squared minus 15I plus 5, dividing by n to the third. And so this is the width of the ith rectangle. And so what it means is this: if let's say we want to know what is the width of the 8th rectangle, and then n would be 8, and then I would be 8. And so we put a here, and then a here, and then evaluate this expression, and that will give us the width of the 8th rectangle. And if we want the width of the 7th rectangle, and then in the place of I, we would put 7, and then n would be 8. And then evaluate this expression, and that will give us the width of the 7th rectangle. And if we look at all the widths, they they're all different. And the last one has the largest width. And that's rectangle number 8. And the value right here, this is 5, and then x of 7, so x of 8 is 5, x of 7 is 3.3496. And so the width of the 8th rectangle will be x of 8 minus x of 7, and that would be 1.65. And so for this particular partition of the interval from 0 to 5, the largest width will be the width of the 8th rectangle, or the 8th subinterval right here. And we have a simple symbol to represent the largest width. We call it the norm of the partition, and it's denoted as the double bars with the delta symbol inside. And so this represents the largest width. And then if we can imagine, if we allow the largest width to approach 0, meaning make the largest width approach 0, make it real small. And so the only way to do that is to allow an infinite number of rectangles inside the shaded region. And therefore, if we allow the largest width, or the norm of the partition, to approach 0, and then n, the number of rectangles, will approach infinity, because the only way to make this small is to fill this shaded region with many rectangles. And so as the norm approaches 0, then the number of subintervals, or number of rectangles, will approach infinity. And now let's go find the area of these 8 rectangles, and so that we can get an approximated value for the shaded region. So let's look at rectangle number 1. So rectangle number 1 is a very small rectangle right here. And the x of 0 is 0, and then x of 1, which is right here, is 0.0097. And so the width of the first rectangle is 0.0097. And to calculate the height of the first rectangle, we will use the right endpoint method, meaning this is 0 and this is 0.0097. We will use the 0.0097 to calculate the height of this rectangle right here. And so we plugged in the 0.0097, and that will give us a y of 0.21. And so right here, this is x of 1, which is 0.0097. The corresponding y is 0.21. And so this point right here has the first rectangle has a height of 0.21, and this is the area of the first rectangle. And now let's go to the second rectangle right here. This is x sub 1, this is x sub 2. X sub 1 is 0.0097, x sub 2 is 0.078, and we will use the 0.078 to find the height of the second rectangle. And so when x is 0.078, we plugged it in here, and that will give us the y of 0.42. And so the height of the second rectangle will be 0.42, since this point right here, the point right here, is x of 0.7 and y of 0.42. And let's find the height of the third rectangle. This is x of 2, and this is x of 3. So this is 0.078, and this is 0.2636. And we will use the right endpoint to find the height. And so we want to find this point right here. And that point is 0.26 for the x and 0.64 for the height. So the height of the third rectangle is 0.64. And that will give us an area of 0.1189. And then the rest of the rectangles, this is area of rectangle number 4. This is area of rectangle number 5. And then rectangle number 6, number 7, number 8, they all can be found similarly. And so these are the values of the 8 rectangles, areas of the 8 rectangles. And then if we add them up, they will come out to be 6.91. And so the area of the shaded region is approximately 6.91. But if we look in the rectangles, they are outside of the shaded region. And so this value of 6.91 will be higher, much higher than the value of the area of the shaded region. And so now let's go fill the shaded region with more rectangles so that we can find a better approximation. And so now this is, instead of 8 rectangles, now is 10 rectangles, and we get sum of areas of rectangle is 6.81. And here's 15 rectangles. And then here's 20 rectangles. And then here's 25. And now let's fill it up with 100. So there's 100 rectangles, and we get an area about 6.45. And so now let's go fill this up with an infinite number of rectangles so that we get the exact answer. And so for 100 rectangles, we get area about 6.45. Once again, the function is the cube root of x, or the third root of x. And earlier we found that x sub I is 5 to the third divided by n to the third. And then earlier we also found the width of the ith rectangle, and that comes out of the 15i squared divided by n to the third minus 15i over n to the third and plus 5 over n to the third. And so now let's get the height of the ith rectangle. And again, we're using the right endpoint method. And so the height of the first rectangle would be f of x sub 1, and then so on. And so in general, it's just f of x sub I. So in the place of x, we'll put x sub I. but x sub I is 5I to the third dividing by n to the third. And so we have the third root, or the cube root of 5, and then the third root of I to the third is I. The third root of n to the third is just n. So the height of the ith rectangle is the third root of 5 divided by n times I. And so, for example, if we want if n is 8, then the height of the eighth rectangle would be the third root of 5 divided by 8 times 8. And now let's find the area of the ith rectangle. So area would be the height times the width. But the width is just this right here. So the height is this expression, the width is this expression. And now let's multiply this out. And so this expression times 15I squared over n to the third, it'd be 15 times the third root of 5 divided by n to the fourth times I to the third. And then this expression times 15I over n to the third, it'd be 15 times n times the third root of 5 divided by n to the fourth. And then this expression times 5 over n to the third, it'd be 5 times the third root of 5 divided by n to the fourth times I. And so this is the area of the ith rectangle. And now let's find the area of n number of rectangles. So this is area of ith rectangle, and then if we want n number of rectangles, areas, then we'll do summation from 1 to n. So this is the area of the ith rectangle, and so this will be the area, sum of areas of n number of rectangles. And then f of x sub I times delta x sub I is this expression right here. This part is constant, and then so we can put it in front of the summation notation. And again right here, this is summation of sum and difference. And so it will be just sum and difference of summations. And then we can move this right here and put it in front of the summation notation. And then move this and put it in front of the summation notation. And then move this and put it in front of the summation notation. So this becomes summation of I to the third, summation of I squared, summation of I. And so we'll need 3 formulas, one for this, one for this one, and one for this one. And so for summation of I to the third, it will be this, it'd be 1/4 n to the fourth plus 1/2 n to the third plus 1/4 n to the second. And then for summation of I squared, it'd be n to the third divided by 3, n to the second divided by 2, and then n divided by 6. And then summation of I is just n to the second and divided by 2 plus n divided by 2. And so in the place of summation of I to the third, we'll replace it with this. In the place of summation of I squared, we'll replace it with this. And then in the place of summation of I, we'll replace it with this. This is what we end up with. And now let's multiply everything out. This expression times 1/4 n to the fourth, the n to the fourth will drop out, and then what's left is just 15 times the cube root of, or the third root of 5 dividing by 4. This expression times 1/2 n to the third be n to the third dividing by n to the fourth. So that's why we have an n in the denominator. And then this expression times 1/4 into the second. Then here we will have n to the second dividing by n to the fourth. And so that will leave it with n to the second on the bottom. And then minus this expression times n to the third over 3. And we will have n to the third dividing by n to the fourth. And so there will be n. And here's a 3, so that's why we get 3n in the denominator. And then this times n squared over 2. Then we do n squared divided by n to the fourth, and there's a 2 here. So that's why we get 2n squared here. And then this expression times n over 6. It'd be n divided by n to the fourth. And then we have a 6 here, so that's why we get 6n to the third. And then the last part, it'd be, if we do this expression times n squared over 2, then there's going to be 2n squared in the denominator. And then this times n over 2 would be 2n to the third in the denominator. And so this right here, this is the sum of areas of n number of rectangles. But since we want exact area, then we need to allow n to run to infinity. And to allow n, to make n go to infinity, we need to allow the norm, or the largest width, to approach 0. And so if we allow the norm, or the largest width, of the partition to approach 0, then that will force n, the number of rectangles, to go to infinity. And that's how we get the exact area. But if n runs to infinity, then this term we get 15 times the third root of 5 dividing by 4. This will go to 0 since we have n running to infinity. This will go to 0, and then everything here will go to 0 since there's an n in the denominator. And so the only thing that does not go to 0 is just the first term. And this comes out to be 6.4124. But this is the exact area of the shaded region. This is a limit quantity, and when it does exist, we'll denote it as the definite integral from a to b. And so in this case, a is 0, b is 5. And the f of x is the third root of x, and then times the differential of x. And so this is called a definite integral, and it represents the value of this limit quantity. In this case, this limit quantity has a value of 6.4124. And therefore, this definite integral right here, it represents the area between the graph and the x-axis. And that area is 6.4124. When we fill when the shaded region was filled with 100 rectangles, we got about 6.45. But the exact answer is 64124. And so as the number of rectangles gets increases, then this number right here, the sum of the areas of the rectangles, will approach the 6.4124.